Okay, let us see these examples when they want us to get the shortest distance and then the shortest time taken for that shortest distance. Okay, so we are going to use here, we're going to focus on the vector approach, then we shall see other methods in the next lesson. So particle P starts from rest at point with position vector 2j plus 2k, means that it has no ith component. So it means the initial position when time is 0, this is going to be the position. With the velocity, so the velocity of P is that. A second particle Q starts at the same time from the point whose position vector is this, with the velocity this. Find the time when they are closest, distance when they are closest together, distance covered by each at that time. Now, remember, if you want the time for the closest distance, we get the relative velocity of those two particles times their relative distance at any time. If we dot them, we get 0. So it means that now we need to get the relative velocity of this n. If you get P of Q, it's okay. And you get also Q of P, it's okay. Just it's going the only difference is going to be the time in the negative or the direction, but they are going to be giving the same answers. So now with this one, remember it's going to be having t. So when we dot this and this, we shall get the value of t, which after will be the one which is giving us the shortest distance. Then after getting this t, we come and substitute in this displacement. Then after that it's modulus, and we shall be getting the distance. Okay, let us start with that. So know that always our P displacement relative to Q is going to be this and this. But remember, Vp minus Vq is equal to our relative velocity of P and Q. So you start by getting this. So P, the velocity of P relative to Q is going to be Vp minus Vq, which will be our Vp 0 minus, and so this will be negative 2, then 0, then negative 1, and this will be meters per second. That's going to be our velocity. So now, after this, we can come and substitute here from our P relative to Q at any time is given by Rp naught, then plus Q, then times T. So here, substitute, we have that already. That is here, 0, 2, 2, the displacement of P initially. Then this one is negative 11. Negative 2, then negative 7, then plus our relative velocity, then times t. Okay. When we simplify this, we are going to get 0 minus minus, we shall get 11, 2 minus minus, which is 4, 2 minus minus, which is 9, then plus, when we open brackets, we get negative 2t, 0 minus t. Then from there, we can every add. So p so that we get 1 vector. So this plus this, we get 11 minus 2t. Then this plus that, we get 4. Then this plus that, we get 9 minus t. Okay, so that is it. So after getting this, we know that now to get our time, we get when we dot the relative velocity times the relative displacement at any time t, we should get 0. So this one is negative 2, 0, negative 1, dot this, equaling to 0. So this would be how we dot, we get this times this, then plus, we are dotting 11 minus 2t, now plus, this times this, that's how we dot, then plus, this times this, negative 1 into 9 minus t, equaling to 0. So this will give us negative 22 plus 4t plus 0 minus 9 plus t equaling 0. From there, hope you can see we are going to be adding 5t minus 32 equaling to 0. And from there, you can able see that our t is going to be 32 divided by 5. I think that's 6 point. Sorry. Negative 22 minus 9. That is a 31, not 32. That's going to be 31. So our t will be now 31 divided by 5, which is 6.2 seconds. So that's the time for their shortest. Remember, this one is meters per second, that's why I have also their seconds. So I have the time, the distance when they are processed together. So if this is the time when they are processed together, it means that if we have this, we can come and substitute here for the distance processed together. Then our part B, remember, so our P relative to Q, the displacement at T is given by 11 minus 2T, then 4, then 9 minus T. So meaning when T is 6.2, that's when you can get the closest distance. Our Q of 6.2 is going to be 11 minus 2 into 6.2. Okay, so from there, this one is going to give us, this will be negative 1.4. This is 4. This is going to be 2.8. So to get now the distance, our distance will be now magnitude of P, Q of 6.2, which will be the square root of negative 1.4 squared plus 4 squared plus 2.8 squared. And so this will give us this will be 5.0794 meters. That's the distance when they are processed. So distance traveled by each at this time. So distance traveled by each means that we need to get R of P at any time. So it's given by R of P initially plus the velocity of P, then times T. So from there, our RP at 6.2 is going to be this at initial 0 to 2, then plus the velocity of P, which is 0, 1, 1, then times into 6.2. And so our R 6.2 here is going to be, so here I want to have a 0, and then 6.2 plus that we have 8.2, then 6.2 plus that we get 8.2. So now our distance, we said distance is the magnitude of this. So 0 squared plus 8.2 squared. And so this will give us so we are getting 11.5966 meters. So that's the distance P had traveled to the time of the distance of the closest approach. Then our R cube at any time, we say it's R of Q initially, the initial position, then plus the velocity of Q, then times, that's our RQ. At this time, it's going to be initial position of Q, -11, -2, -7, then the velocity of Q, (6.2), and this RQ is going to be now 1.4. Then this one is going to be 6.2 minus 2, that's 4.2. Then this is going to be 12.4. minus 7, 5.4. Our distance. Always, whenever I want to get a distance, you get the modulus of the displacement. This displacement, 1.4 squared, the whole squared, and this is going to give us 6.9828 meters. So that's the distance. Those are the distances they are traveled before the point or before this time when they are close to each other. So that's how we had that. I wish you well. The next lesson now, this is the vector approach. The next lesson we are going to see other approaches, but I think this one is the easiest by now. See you there.